So in the previous lecture, we had begun treatment for considering the rigid diaphragm action of the floor slab. Basically, the floor slab introduces a compatibility condition that any 2 points lying on the floor slab will undergo translation and rotation in such a manner that the relative distance between the 2 points does not change. That is, we can consider that the floor system, it undergoes a displacement like this. So we can view it that the entire floor system is undergoing rotation about an external point like this. Alternatively, we can consider a reference point within the slab, and we can then express the displacements of all other points in terms of the displacement and rotation of the reference point lying on the floor slab itself. We can choose this point as the origin of the coordinate system itself. So phi is the rigid body rotation, and all the displacements and forces corresponding to the floor degrees of freedom, they need to be transformed to the floor reference point. So this point is arbitrarily chosen. It can be same as the origin of the coordinate system, but it should not be confused as the center of rotation of the entire floor system. We do not have any information about the external point about which the floor system is rotating as a whole. So how do we do it? We have to introduce this kind of transformation. All we need to now do is express the displacement of any arbitrary point, say j, in terms of the displacements of the reference point. So for this purpose, all we do is that we join the point j with the reference point, and if the floor system undergoes a rigid body rotation phi, and assuming that phi is very small, then the arc length and the tangent lengths, they can be considered same. If we just zoom this portion, then this is how it looks like. So the translation undergone by point j, which has now moved to j dash, is basically r times the rigid body rotation, and this can be split into 2 components, one in the x direction and other in the y direction. So the y component is basically the cos theta component. Basically, theta is the angle which the line joining the reference point with point j makes with the x-axis, and similarly in the other direction, this is the sine component, and our sine theta is nothing but the value of y. So we need to express all the displacements of this point j in terms of the reference point O1. So this is now fairly simple once we have understood how the slab translation and rotation takes place. So in the x direction, the displacement of point j can be expressed as follows. So this is equal to the translation of the reference point minus y coordinate times the rotation phi. So here this d1j refers to the joint being considered, and d1 star refers to the displacement of the reference point. So we will be assigning star with all the displacements and rotations concerned with the reference point. In y direction, we can write in the same manner. So d2 star is the displacement in the global y direction of the reference point. We have added here x coordinate multiplied by the rotation. Finally, the rotation at point j is same as the rigid body rotation of the entire floor slab, and this is shown by this equation that d6j is same as d6 star, that is the reference point. So in this way, what we have done is that we have expressed the displacements of any arbitrary point j in terms of the displacements, both translations and rotations of the reference point. So similar transformations, they are needed at the other end of the members. So let's see that let's say we have this structure and we just isolate member number 1, which is a beam, and here we have shown the member degrees of freedom from 1 to 12, and we can also show similarly the structure degrees of freedom in terms of the displacements of the floor slab and also the joint displacements. So here are the structural degrees of freedom, and by this you can form the association matrix of this particular member. So all we can find is that the degree of freedom 1 corresponds to 28, but at the same time degree of freedom 7 also corresponds to 28, because they both refer to the reference point. Hence, at the time of assembling, the terms of the member stiffness matrix in global coordinates corresponding to 1 as well as 7, they will both land up at the same location in the total structure stiffness matrix. However, we need to do transformation of the stiffness matrix of the member before we can transfer the elements. Now this transformation has to take into account the rigid body diaphragm action of the floor slab, because in our present formulations we are considering the displacements, the floor degrees of freedom at the reference point. Similarly, the member end forces also need to be transformed to this particular point. So now, taking both the ends of the member into account, we can write these equations that d1 is equal to d1 star minus yi into d6 star, and we can express it because now we have the association matrix in terms of the structure displacements, and similarly for d2 and d6. And at the other end of the member also we can write similar equations in terms of the floor and the joint degrees of freedom. So you can just take a pause to verify your equations, because now 1 and 6, they correspond to 28 and 30 respectively, as we can see from the association matrix. And similarly 2 corresponds to 29 and then 12 corresponds to 30. So this information can be easily visualized from this matrix. So this transformation can be written in a matrix form like this. So here we are showing the corresponding floor degrees of freedom also. So this transformation matrix has most of the members 0, except here we have xi, yi and xj, yj, and of course for yj we have minus sign, and we have already seen why there is minus sign. So this can be expressed in compact form like this. So what we have done is that we have expressed the absolute displacements of the ends of the member in terms of the displacements of the reference point, and for this purpose we have introduced this matrix C. So this takes into account now the in-plane rigidity of the beams in an automatic fashion, because now the two endpoints of the beam will undergo displacement such that the relative distance between them remains unaltered. So as a result, the axial force and the lateral bending moment is 0. This matrix C is called as the displacement transformation matrix. So it basically transforms the displacements at the two ends of the member in terms of the displacements of the reference point. Similarly, we need to carry out force transformation also. Let's say there are forces at the member ends, and these forces corresponding to the floor degrees of freedom, they need to be transformed to the reference point. It's not necessary to transform the other forces which are corresponding to the joint degrees of freedom, but the 6 floor degrees of freedom, they need to be transformed to this point. So this is also fairly easy. So if we have to transform the force, say the joint is located here, and the forces, when they are transformed parallel to themselves, they will introduce a moment. So that is the only correction required. So for example here, the force at the reference point is just equal to the force at the member end in both the global x and y directions, but then the correction has to be there in the case of the moment, because we have shifted the forces, so a moment is introduced. Similarly, at the other end we can write in the same fashion. The forces, they remain same, F7, F8, but the shifting of the forces, that introduces moment. So what we can see is that the force in the global x direction, that is subtracted because it introduces a moment in negative z direction, but the force in the positive y direction, it introduces a moment in the positive z direction. So why this happens, we can see that if we have a force and if we wish to shift the line of action of the force, then what we do, we introduce a set of equal and opposite forces. And now what we do, we just club these two forces and make it a moment like this. So that's the reason why a moment is introduced when we shift the line of action of the forces. Since this force is in the positive x direction, so its shifting has introduced a negative moment. Similarly, if the force is in the positive y direction, it will introduce a positive moment. That's what we have seen here. So we can write the equation in the same manner just we have written for the displacement transformation. So only thing is that here C transpose comes, the terms xi, yi, xj, yj, they remain similar, and this is now the force transformation matrix. So force transformation and the displacement transformation matrices, they are just the transpose of each other. Now once we have done this, we can now modify the 12 by 12 stiffness matrix of the member. So we have the stiffness matrix of the member in local coordinates, then we transform it in the global coordinates, and after this we introduce the displacement transformation, and then we introduce the force transformation. So now we have the equation for the force transformation, and we can substitute the expression for force vector from this equation, then we get this kind of result. So what this shows is that the forces and the displacements, they are now transformed forces and displacements referring to the reference point. And for this purpose, we need to pre-multiply the stiffness matrix of the member in global coordinates with C transpose and post multiply it by C. So it's important to now recognize that by this transformation, the presence of the floor slab is now taken into account. Now let's see the implications of the transformation on beams. So essentially, in the case of beams, the two ends of the beam, they undergo same amount of rotation in the horizontal plane. As a result of this, the beam does not have any lateral bending moment. In the plane of the floor slab, the beams undergo displacement such that the relative distance between the two ends remains same. As such, they will not have any axial force. So essentially, a beam member has 6 degrees of freedom. 2 degrees of freedom, they correspond to the vertical displacements, and then the other 2, they refer to the rotations. For example, for member B, we have shown these 6 degrees of freedom like this, but actually we are achieving this effect on 12 by 12 matrix through geometric transformation. We will not reduce the matrix to 6 by 6. So after this transformation, we have seen that the beam does not have any lateral bending moment and the axial force. But how about torsion? Will torsion be there or not? The answer is that torsion is not eliminated. The beam still has torsion. So if the beam is connecting two columns, they undergo different rotations normal to the plane of beam, then these differential rotations will give rise to torsion. So this kind of torsion is called as compatibility torsion. IS 456 gives flexibility to the designer that he has option of considering either the torsional constant J as 0 or a finite value. If the torsional constant J is considered 0, then the beams will not have any compatibility torsion, but if the value of the torsional constant has been considered, then the analysis output will show torsion in the beams. So in this particular situation, the beams have to be designed for torsion also, just like the code recommends converting the torsion into equivalent bending moment and shear force. So the rigid body moment of the beams can be understood in simple terms also, that because the two ends of the beam, they have undergone same horizontal rotation, and as a result of that, the lateral bending moment is 0, because the beam as such remains straight. Now for the case of the columns, the endpoints of the columns, they lie on different floors. So the transformation on the columns will not inhibit axial force and any kind of bending moment. So the columns, they will continue to experience biaxial bending moments in addition to axial forces. However, the member end forces and the displacements, they need to be transformed to the reference points because the floor degrees of freedom are being considered at the reference point only. So from the two endpoints of the column, the displacements and the forces, they need to be transformed. The unique feature of columns is that column being a vertical member, the x and y coordinates at the two ends of the column, they are one and the same. So xi and xj will be same, yi and yj will be same. So here we are showing the member and the structural degrees of freedom. For simplicity, we have clubbed together the degrees of freedom corresponding to the floor and the ones corresponding to the joint. So you can yourself see the correspondence between the member and structural degrees of freedom. For example, for the bottom joint, we are seeing here the structural degrees of freedom 1, 2 and 3 and 25, 26, 27. So they are marked here, and here we have marked the member degrees of freedom from 1 to 6. So 1 and 2 we have shown here, and we have clubbed it with 6. 6 is the rotation. So these are deliberately clubbed so that the floor degrees of freedom, they are together just like the structural degrees of freedom. So unlike beams, column will continue to have 12 degrees of freedom only. And you can take a pause and form an association matrix of this member. Now in the end, we also need to transform the direct joint loads. So direct joint loads, they may be acting at various joints. So those joint loads which are corresponding to the floor degrees of freedom, they need to be transformed to the reference point, because the entire force vector has to be transformed to the reference points. So for this purpose, we again do the same kind of transformation. So the forces, they can be shifted parallel to themselves, but in the process they will introduce moment. So all we have to do is we introduce a pair of equal and opposing forces, and then we club these forces as moment. So when the force is transformed parallel to itself, it creates moment. So the transformed joint loads, they would be like this. The x and y direction forces, they will be same, and the moments, they will be different because of the transformation of the forces shifting their lines of action parallel to themselves. So thank you very much. So we will meet in the MS Team channel for clearing further doubts.